13 suns share a single sky. This is not science fiction, but the reality of a Tredecuple star system, one of the rarest and most extreme families in the cosmos. By the end of this journey, you will know 25 of the strangest truths about how these stellar giants live, dance, and die. We will uncover how planets might form in such chaos and why some stars are violently flung into the eternal dark. How does a cosmic family with 13 members avoid tearing itself apart? What kind of light show would you see from a world with 13 sunrises? The universe holds configurations so complex they make our single sun seem lonely. What do you think is the most beautiful form of chaos? That first confirmed system carries a name that sounds like a secret, AR Cassiopeiae. It is the Rosetta Stone for understanding stellar families of unimaginable scale. For centuries, observers saw it as just another twinkling point within the constellation of the Queen, but modern astronomy revealed a cosmic Russian nesting doll. At its heart are 3 stars locked in a tight, frantic dance, orbiting each other so closely they are nearly touching. This central trio is not alone, however. It is gravitationally bound to a wider network of other multiple star systems, a grand celestial clan that, when every member was finally counted, numbered exactly 13. Untangling this knot required more than just powerful telescopes. Astronomers turned to the starlight itself, using spectroscopy to split it into rainbows. By watching how those rainbow lines shifted and wobbled over years, they could detect the hidden gravitational tug of invisible companions. They combined this with precise astrometry, measuring the tiniest wobbles in the star's position against the distant background. It was a forensic puzzle, pieced together one orbital clue at a time across decades. Confirming all 13 components was a monumental task because most of these stars are not visible individually, even through our best instruments. We know they are there only by the ghosts they leave in the light of their brighter siblings. This painstaking work set the stage for a stunning realization. If a system this complex and delicate can exist, surviving for billions of years, then the universe permits a form of chaos far more intricate and stable than we ever dreamed. The key to this celestial ballet lies in a principle of cosmic architecture called hierarchical stability. Think of it not as a chaotic free-for-all with 13 stars crashing together, but as an exquisitely organized dance on multiple levels. The most common building block is the binary pair, 2 stars locked in a tight, intimate orbit around a shared center of gravity. In a Tredecuple system, these binaries often form the first layer. Sometimes a third star joins to create a tight triple at the system's heart, like the central trio in AR Cassiopeiae. This is where the Russian doll analogy becomes perfect. That tight triple does not just exist in isolation. It, as a single gravitational unit, then orbits another binary pair at a much greater distance, and that new, larger group of 5 stars might then orbit another distant pair, and so on, building up the family to 13 members through these nested layers of motion. It is a solar system within a solar system within a solar system. The gravitational glue holding it all together weakens with each step outward, but the structure remains intact because the inner dances are so much faster and tighter than the grand, slow waltzes of the outer layers. This hierarchy prevents catastrophic close encounters. Stars in the same tight binary are like partners in a frantic spin, while their entire duo sweeps in a wide, slow circle around another pair, like 2 spinning dancers orbiting another couple on a vast ballroom floor. This intricate choreography is what allows such extreme multiplicity to survive across cosmic time. Yet it is not a perfect, eternal clockwork. The gravitational influence of so many bodies creates constant, subtle perturbations, tiny nudges that build up over millennia. This turns the entire system into a dynamic puzzle for astrophysicists. Running simulations forward millions of years reveals a fascinating truth. some orbital configurations prove to be remarkably stable, settling into a rhythm that can persist for the lifetime of the stars. Others, however, contain the seeds of their own destruction. A star in a particularly sensitive outer orbit might receive one gravitational nudge too many from its siblings. Over eons, these small kicks can add up, accelerating the star until it reaches escape velocity, flinging it out of the family forever into the interstellar void. So within the apparent stability of the hierarchy, there is a slow, relentless game of gravitational dice being played, which orbits are safe and which are doomed. This cosmic dance of 13 suns presents one of the greatest puzzles in astrophysics. Can planets ever form here? In our own quiet solar system, planets were born from a calm, dusty disk that swirled placidly around our infant sun. Dust grains gently collided and stuck together, building pebbles, then rocks, then planetary cores in a serene nursery. Place that same disk inside a Tredecuple system, and you introduce pure chaos. The gravitational tides from 13 different points of mass would constantly twist and warp the disk, stirring the material like a spoon in turbulent water. Just as a planetesimal begins to coalesce, a close pass from a stellar sibling could rip it apart or fling it out of the system entirely. Furthermore, the intense and varied radiation from so many stars, each with its own temperature and stellar wind, would blast the disk, evaporating lighter elements and making it incredibly difficult for material to cool and solidify. The traditional, gentle model of planet formation seems utterly impossible in this environment. Yet nature is ingenious, and astronomers theorize about two potential pathways for worlds in this maelstrom. The first is the concept of a circumbinary planet, but on a staggering scale, a circum-multiple planet. This would be a world that orbits so far out, it treats the entire central cluster of stars as a single, combined gravitational mass. From that immense distance, the complex inner dances of the 13 stars blur into one average point of gravity, potentially allowing a stable orbit far beyond the fray. The second, more exotic possibility involves planets that are not born there at all, but are captured. A rogue planet wandering the interstellar void could be gravitationally snared by the system's powerful net, becoming a permanent, distant member of this stellar family. The most likely truth, however, is that these systems are planetary deserts. The constant gravitational churning may prevent any stable congregation of material, leaving behind only the stars themselves in their intricate hierarchy. This leads to a haunting question: if a planet did somehow form or survive in such a place, what kind of sky would it see? The light from a Tredecuple star system is never still. It is a symphony of shadows, a cosmic light show of staggering complexity. From our distant vantage point, the combined glow of 13 suns flickers and dances in a pattern that defies simple prediction. This is because eclipses and occultations are not rare celestial events here. They are the constant background rhythm of daily life. As the stars whirl around each other in their nested orbits, they are forever passing in front of and behind one another from our perspective, each transit casting a tiny, precise shadow. The result is a light curve, a graph of brightness over time, that looks less like a steady line and more like the frantic scribble of a seismograph during an earthquake. This flickering beacon is both a nightmare and a treasure trove for astronomers. Decoding it is like listening to 13 overlapping songs at once and trying to separate each individual instrument. Yet within that chaos lies the system's most revealing fingerprint. The deepest, most regular dips in light often come from the innermost, tightest binary pairs. When two stars orbit incredibly close, they frequently eclipse each other, causing dramatic, periodic drops in brightness. These are the primary beats of the rhythm. But superimposed on those regular beats are slower, subtler waves, caused by the wider orbital pairs where one star may take years to pass in front of its distant companion. Then there are the unpredictable flickers, the tiny dips and bumps created when a star in an intermediate orbit briefly grazes the light of another. Analyzing this data is a monumental exercise in cosmic forensics. Astronomers feed the wild light curve into sophisticated computer models, testing millions of possible orbital configurations until they find the one dance that perfectly reproduces the observed pattern of shadows. Each dip in light is a clue, each subtle change in the curve a hint about a star's size, temperature, and path. Through this painstaking process, the invisible architecture of the entire 13-star family is slowly, miraculously drawn out from the shadows. The constant gravitational nudges within this stellar family have a dark and dramatic consequence. While the hierarchical dance provides stability for most, it also sets the stage for cosmic exile. In a system with 13 massive bodies, close encounters are inevitable over billions of years. When two stars in different orbital layers pass just a little too near, they engage in a gravitational slingshot. Energy is exchanged, a subtle theft of momentum. One star might be slowed, sinking deeper into the system's gravitational well, while the other is catapulted outward with terrifying speed. If that speed exceeds the system's escape velocity, the star breaks free entirely, becoming a runaway. In the most extreme cases, the ejection is so violent it creates a hypervelocity star, a solitary sun hurtling through the galaxy at speeds that can exceed 1,000,000 miles per hour. This is not a gentle drift into the night, it is a violent expulsion, a stellar refugee cast out from its chaotic home. Astronomers find evidence for these events by tracing stellar trajectories backwards. They have observed lone stars, often young and blue, racing through the galactic outskirts on paths that, when rewound, lead directly back to the dense cores of star clusters or the locations of known complex systems. These are the cosmic breadcrumbs pointing to a moment of catastrophic gravitational interaction. The ejected star carries the signature of its origin in its speed and its composition, a permanent record of the violent physics that forged its fate. This leads to a profound thought. As we look up at the Milky Way among the countless points of light, some are not born in solitude. They are the survivors of a stellar war, the orphans of a family too large to hold together. Every rogue star screaming through the dark might be a silent testament to a Tredecuple system that once was, a puzzle that slowly unraveled itself across the eons, scattering its pieces into the void. The sheer number of stars in these systems guarantees a menagerie of cosmic oddities. With 13 members, the probability of finding exotic stellar pairings and extreme stellar types is not just high, it is almost a certainty. These are not families of identical twins, but sprawling clans containing stars in every stage of life, from violent newborns to ancient, fading embers. Astronomers have begun to catalogue the strange demographics within these systems, and the findings rewrite the rules of stellar families. One of the most dramatic pairings possible is a binary consisting of two massive O-type stars. These are the titans of the stellar world, burning ferociously hot and blue, and destined for short, explosive lives ending as supernova. To have two such behemoths locked in a tight, frantic orbit is a recipe for cosmic fireworks. Their mutual gravitational pull distorts their shapes, and they likely exchange massive streams of superheated gas, shrouding the pair in a shared, turbulent atmosphere. This dance cannot last long on astronomical timescales, and its end will be spectacularly violent. In stark contrast, other corners of the same Tredecuple system might host a quiet, elderly couple, a red giant and a white dwarf. The red giant is a swollen, cooler star in its final stages, having exhausted its core fuel, while the white dwarf is the exposed, super-dense core of a star that has already died. Their coexistence tells a story of vastly different life cycles playing out within the same gravitational domain. Perhaps the most intriguing discoveries are the pre-cataclysmic variable pairs. These are binary stars so close that one star, often a red giant, is actively spilling its outer layers onto a white dwarf companion. This is the calm before a stellar storm, a slow-motion prelude to a potential cataclysmic event. Over eons, as more and more hydrogen accumulates on the white dwarf's surface, it could trigger a runaway thermonuclear explosion, a nova, or in extreme cases, push the white dwarf over a critical mass limit, causing a Type I supernova that could rip the entire system apart. Finding such a volatile pairing nestled within a larger family of 12 other stars adds an incredible layer of long-term instability to the system's fate. This incredible diversity of stellar ages and types presents a profound puzzle. Standard models of star formation suggest that stars in a single system are born together from the same cloud of gas and dust, making them roughly the same age. A Tredecuple system containing both short-lived O-type stars and long-dead white dwarfs, objects billions of years apart in age, shatters that model. The inescapable conclusion is that these systems are not simple birth families but gravitational zoos. They are cosmic collectors, entities whose powerful gravity has, over billions of years, captured wandering stars of all ages and types that happen to pass too close. The system we see today is not a snapshot of a single moment of creation, but a layered archaeological record of captures and mergers, a celestial museum where each star is an artifact from a different epoch, all now bound together in an unstable, glorious dance. Amidst this stellar chaos, a different kind of structure emerges from the wreckage. While full-fledged planets may be a rarity, many of these 13 star systems are not empty. They are filled with vast, swirling graveyards of dust and shattered rock, immense debris disks that glow with the ghostly heat of countless collisions. Seen in the infrared, these disks are not the smooth, serene rings of our solar system's asteroid belt. They are twisted, warped, and punctuated by strange clumps and gaps, sculpted by the relentless gravitational hands of 13 sculptors. The radiation pressure from stars of different temperatures pushes finer dust into complex spirals, while the gravity of individual stellar pairs carves out clear lanes like celestial sheepdogs herding particulate matter into narrow bands. This creates a dynamic, ever-changing landscape where mountains of rock and ice are constantly being pulverized, a collisional environment of unimaginable ferocity. The true spectacle, however, would be in the play of light. From within such a disk, the sky would be a theater of multiple shadows. As one binary pair eclipses another from the perspective of the dust cloud, a vast, dark wedge would sweep across the debris field, cooling it momentarily. Then, from another angle, a different star might cast the elongated shadow of a companion onto the disk, creating a moving silhouette that dances over the rocky terrain for years. These are not static patterns, but a luminous, slow-motion shadow play orchestrated by the orbits of all 13 suns. The very structure of the disk, therefore, becomes a historical record. Its warps and gaps are not random. They are a frozen map of gravitational resonances, pointing directly to the masses and orbits of the stars that made them. By studying the twisted geometry of these dusty shrouds, astronomers can infer the presence and influence of stellar members that might otherwise remain hidden, reading the history of the system's gravitational tides written in stone and ice. The most intimate stellar bonds can become a slow-motion act of cosmic cannibalism. Within the crowded hierarchy of a Tredecuple system, the tightest binary pairs often engage in a bizarre and violent exchange of life itself. When two stars orbit incredibly close, the gravitational dominance of the denser star can literally tear the atmosphere away from its larger, more bloated companion. This is not a gentle drift, but a torrent, a superheated river of hydrogen and helium plasma screaming across the void between them. Astronomers discovered these mass transfer streams not by seeing them directly, but by listening to the star's light. When they split the system's combined glow into a spectrum, they found strange, shimmering emission lines, bright fingerprints of specific gases like hydrogen alpha. These lines were not just present, they were Doppler shifted, showing one part of the gas stream rushing toward us at hundreds of thousands of miles per hour and another part rushing away. It was the spectral signature of a whirlpool, a hurricane of stellar material being siphoned from one sun to feed another. Where this river of stolen gas lands, it does not fall quietly. The incoming material, carrying immense angular momentum, swirls around the receiving star, forming a furious, flat vortex called an accretion disk. This disk glows with blistering heat from the friction of countless collisions, often outshining the star it orbits in X-ray and ultraviolet light. For a time, this setup can create a periodic nova, as hydrogen piles up on the surface of a dense white dwarf star within the binary. Pressure and heat eventually trigger a thermonuclear explosion, blasting the accumulated material into space in a brilliant flash that can be seen across the galaxy. But in the tightest binaries, the story does not end there. The transfer of mass changes the fundamental dance. As the donor star loses material, it loses gravitational influence while the gaining star becomes more massive and its grip tightens. This can shrink the orbit further, accelerating the transfer in a runaway feedback loop. The result is a stellar merger, a cataclysmic embrace where two stars become one in a violent outburst of light and ejected material. Now, imagine this incredibly violent process not happening in isolation, but in a delicate mobile of 13 stars. The sudden flash of a nova, or the far greater gravitational jolt of a merger, sends a shockwave through the system's fragile hierarchy. It is like suddenly replacing one of the spinning dancers in our cosmic ballet with a different, heavier partner mid-trance. The delicate balance of gravitational resonances that has kept the outer stars in their stable, slow orbits for eons is shattered in an instant. Simulations show such an event could fling entire binary pairs out of the system, send solitary stars careening into new, chaotic orbits, or even trigger a chain reaction of destabilization that reconfigures the entire family tree. A single act of stellar vampirism in one corner of the clan could rewrite the destiny of all 13 suns, proving that in these complex systems, no star lives or dies alone. The most violent stellar mergers are not the end of the story, they are the beginning of something even more profound. When a binary pair containing two incredibly dense stellar corpses, like neutron stars or black holes, survives within a Tredecuple system, it becomes something far more potent, a gravitational wave factory. These are not the catastrophic bursts of waves from a single collision, but a continuous, low-frequency hum, a permanent distortion in the fabric of spacetime generated by their endless, frantic orbit. Imagine the tightest binary pair in the entire 13-star clan, two city-sized neutron stars separated by less than the distance from the Earth to the Moon, whirling around each other at a significant fraction of the speed of light. Their immense mass and incredible velocity make them perfect engines for rippling spacetime itself. Each orbit sends out a wave, a literal tremor in the cosmic grid that propagates outward at the speed of light. This is the universe's most fundamental form of communication, a broadcast written not in light but in the bending of geometry. The chaotic environment of the Tredecuple system acts as a cosmic accelerator for this process. The constant gravitational nudges from the other 11 stars in the hierarchy act like tiny, relentless taps on the shoulders of this dancing pair. These perturbations can slowly tighten their orbit, feeding energy into their spin and hastening their ultimate in-spiral. Over millions of years, what might have been a slow decay becomes a quicker march toward collision, all because of the crowded stellar neighborhood they call home. While our current gravitational wave observatories are tuned to hear the final, catastrophic chirps of merging black holes, the next generation of instruments aims to listen for this continuous hum. It would be a low, steady thrumming beneath the more dramatic bursts, a background chorus contributed by all the compact binaries in our galaxy. including those hidden within systems of extreme multiplicity. To finally detect that hum would be to hear the Milky Way not as a silent picture, but as a living, vibrating entity. It would mean the intricate, invisible dance of a Tredecuple star system, with all its 13 moving parts, is not just a visual spectacle or a gravitational puzzle, but a contributor to a symphony felt across the very dimensions of space and time. The gravitational ballet of 13 suns creates a landscape of shifting balance points. In any two-body system like the Earth and Sun, there exist 5 special locations called Lagrange points. These are positions where the gravitational pull of the two bodies perfectly balances with the centrifugal force of a smaller object's orbit, creating zones of relative stability. A classic example is the Sun-Jupiter system, where thousands of asteroids known as Trojans are trapped in stable orbits at Jupiter's Lagrange points, leading and trailing the giant planet in its path. In a Tredecuple system, however, this simple concept explodes into fractal complexity. With 13 massive bodies, each binary pair and each higher-level orbital combination generates its own set of these theoretical balance points. The result is not a map of 5 stable harbors, but a dense, shimmering cloud of hundreds, even thousands, of overlapping and competing Lagrange points. The stability they offer is an illusion, a fleeting moment in a gravitational storm. Because every star is constantly moving, tugged by its many siblings, each Lagrange point itself wobbles, shifts, and sometimes winks out of existence entirely as the orbital geometry changes. This creates a dynamic maze where the rules of motion are rewritten with every passing year. Within this chaotic lattice, astronomers theorize a strange, transient population could exist. Imagine an asteroid or a concentrated cloud of dust wandering in from the outer reaches of the system. Instead of being flung out or crashing into a star, it might be momentarily captured by one of these shifting balance points. It would not settle into a peaceful, permanent orbit like Jupiter's Trojans. Its residency would be temporary and tumultuous. As the stellar dance continues, the Lagrange point that captured it will distort and vanish, ejecting the asteroid. But in this crowded gravitational field, it is almost immediately confronted by the influence of another stellar pair. Simulations show these objects can be passed like a chaotic cosmic pinball, bouncing from the unstable Lagrange point of one binary to the transient zone of another. They become a swarm of transient Trojans, never truly belonging to any one star, but instead engaged in a dizzying, unpredictable dance through the interstices of the entire family. These would not be permanent features, but ghostly apparitions, clouds of rock and ice that coalesce and disperse within centuries, mere flickers in the multi-billion-year life of the stars. Their existence, though likely brief, would paint the space between these 13 suns with an ever-changing filigree of captured debris, a testament to the impermanent pockets of order that can arise, however briefly, within the most profound chaos. The light from these systems is a beautiful lie. When we point a telescope at a Tredecuple star, we capture not a single pure color, but a blended cocktail of 13 different stellar signatures, a composite glow that can deceive the eye. To the unaided telescope, it might appear as a single, steady point of white or pale yellow light, giving no hint of the pandemonium within. The truth is only revealed when astronomers pass that light through a prism, splitting it into a full spectrum rainbow. What they find is not a clean series of dark lines marking specific elements, but a dense, tangled forest of overlapping absorption lines, a spectral traffic jam where the features of 13 suns are superimposed. A hot, massive O-type star leaves the deep, broad fingerprints of ionized helium. A cooler, aging red giant imprints the delicate lines of molecules like titanium oxide. Their light combined creates a chaotic barcode that seems impossible to read. Disentangling this spectral knot is one of the most painstaking tasks in modern astrophysics. It begins with recognizing that each type of star has a unique pattern, a spectral template based on its temperature and gravity. Astronomers must take the messy, combined spectrum and mathematically subtract the template of the brightest star, then the next brightest, peeling away layers of spectral influence like an onion. They rely on the Doppler shift, watching how groups of lines belonging to one star rhythmically shift toward the blue as it moves toward us, then to the red as it moves away, tracing out its specific orbital dance. This process is repeated for every suspected component, a computational puzzle where a single misstep can assign a line to the wrong star and unravel the entire model. The goal is to isolate from that single beam of blended light 13 individual rainbows, each telling the story of a different sun. This spectral chaos has a direct, visible consequence. These systems often exhibit a strange, indefinable color. They are not purely blue from hot stars, nor purely red from cool ones. They are a shifting, composite hue that astronomers sometimes call interstellar beige or a metallic gold, a color that has no simple name because it is not born of a single source. This perceived color can even change subtly over time, not because the stars themselves change color, but because of the eclipses within. If a particularly brilliant blue star is momentarily hidden behind a larger, cooler orange sibling, the system's combined light temporarily reddens. When that blue star re-emerges, the balance tips back. The system itself flickers in hue, a slow, cosmic mood ring responding to the hidden alignments of its 13 faces. Observing this requires patience, measuring the color with exquisite precision over years to detect the gentle waves of change imprinted by the orbital clockwork. It is a reminder that the light reaching us is a final, blended performance, and behind that curtain, 13 distinct performers are forever entering and exiting the stage. The blended light hides another invisible force shaping this stellar chaos. Beyond gravity, the stars are bound by webs of magnetism, fields of immense power that can tangle and snap with terrifying consequences. Many stars, like the energetic red dwarfs or the swollen red giants often found in these systems, possess magnetic fields thousands of times stronger than our Sun's. In the solitude of deep space, a star's magnetic field is its own sovereign domain. But place 13 such monarchs in a crowded gravitational court, and their magnetic kingdoms begin to collide. The invisible lines of force extending from each star do not simply stop at a boundary. They stretch out into space, intertwining with the fields of their closest neighbors. This can create temporary magnetic bridges, arches of invisible force connecting stellar atmospheres across millions of miles. Along these bridges, superheated plasma can flow, a second, more ghostly form of mass transfer that doesn't require a gravitational bond. The real danger, however, lies in what happens when these tangled fields suddenly reorganize. The process is called magnetic reconnection. When the field lines from two different stars become twisted and strained beyond their limit, they can snap and reconnect into a simpler, lower energy configuration. This sudden release is catastrophic. It converts immense magnetic energy into kinetic heat and radiation in an instant, triggering a stellar flare of unimaginable scale. In a Tredecuple system, a reconnection event might not involve just two field lines from a single star. It could involve the contorted fields of 3 or 4 stars in a tight orbital group, leading to a super flare, an eruption that would dwarf anything our Sun has ever produced. We have evidence this is not just theory. Astronomers point their radio telescopes and X-ray observatories at these complex systems and detect something peculiar. They see bursts of intense, non-thermal radio emission, the telltale signature of electrons spiraling at near light speed along magnetic field lines. They also detect flickering, high-energy X-rays that suggest constant, low-level reconnection is happening, a permanent storm of magnetic fireworks. For any hypothetical world in this system, this magnetic pandemonium would be a constant existential threat. The radiation from a single superflare could strip away an atmosphere in hours and sterilize a planetary surface. The steady drizzle of high-energy particles from these tangled fields would create permanent global auroras while bombarding the planet with a mutagenic rain. Life as we understand it would find no shelter here. The dance of 13 suns is not just a gravitational ballet. It is a storm of invisible forces where the very space between the stars crackles with pent-up energy waiting for a trigger. These overlapping magnetic fields create a hidden architecture of stress, but the gravitational tides themselves hold an even more precise, cyclical form of violence. Deep within the nested orbits of a Tredecuple system, a sophisticated gravitational dance known as the Kozai-Lidov mechanism plays out, but here it is amplified to a terrifying degree. Normally, this is a three-body effect. Imagine a tight binary pair and a third, much more distant star orbiting them both. The distant star's gravitational tug does not just pull, it rhythmically perturbs the inner binary's dance. Over thousands of years, it causes a periodic exchange, trading the inner pair's orbital inclination, their tilt relative to the wider orbit, for eccentricity, the ovalness of their path. As the inclination drops, the eccentricity soars. The two inner stars, which normally orbit each other in a near circle, are driven into an extreme ellipse. They spend most of their time far apart, but at their closest approach, called periastron, they hurtle past each other at terrifying speed, separated by a mere fraction of their usual distance. In a system of 13 stars, this is not a single, isolated interaction. It is the Kozai-Lidov mechanism on steroids. Multiple hierarchies can experience it simultaneously. A tight binary in the system's core might be perturbed by the combined gravity of a wider triple, which itself is being perturbed by an even more distant pair. The effects can cascade, resonate, and synchronize. This can drive inner binaries to eccentricities so high they approach almost one, meaning their orbital path is a needle-thin ellipse. The consequences of these cyclical close passes are dramatic. During each periastron, the stars experience immense tidal forces. Their shapes are stretched, their interiors churned, generating ferocious internal heating far beyond their normal nuclear fusion. If one star is a red giant with a distended atmosphere, these close passes can strip away its outer layers without the need for direct contact, feeding a sporadic, orbit-pulsed stellar wind. If the binary contains compact objects like neutron stars, the periodic close encounters can rapidly accelerate the emission of gravitational waves, hastening their ultimate merger. Most dramatically, if the eccentricity is driven high enough, the stars at periastron may not just pass close, they may actually graze or collide. This turns a stable, long-term binary into a time bomb on a grand, multi-millennial clockwork, where calm stretches of centuries are punctuated by brief eras of extreme stellar violence. The entire system becomes a symphony of these cycles, with different pairs reaching their own moments of peak tension at different times. A celestial calendar of recurring crises written not in years, but in the slow exchange of inclination for a deadly, intimate embrace. These cycles of gravitational tension leave their mark on the very surfaces of the stars. The constant tidal kneading from multiple companions does more than just heat a star's interior. It stirs the cosmic pot where its magnetic field is born. Deep within a star, the churning of plasma acts like a dynamo, generating immense magnetic loops that can erupt through the surface. In the strained environment of a Tredecuple system, this dynamo can be supercharged. The result is stellar activity on a scale that dwarfs our own sun's quiet cycles, manifesting in features of almost unimaginable size. Astronomers have detected evidence of supersized star spots, dark, cooler regions on a star's photosphere that are the footprints of these intense magnetic fields. Our sun's sunspots can be large enough to swallow the Earth whole, but in these complex systems, the spots are thought to be monsters. By analyzing the subtle, recurring dips in a system's intricate light curve, scientists can infer their presence. As a star rotates, a gigantic spot on its surface moves into and out of view, causing a slight, periodic dimming in that star's specific contribution to the total light. Untangling this signal from the forest of eclipses is a Herculean task, but the data suggests some of these spots could cover a significant percentage of the star's face, perhaps 10 or even 20%. That is not a blemish, it is a planetary-scale continent of magnetic shadow. The driving force behind these behemoths is likely the gravitational tides. Just as the moon's pull stirs our oceans, the combined, rhythmic tug of multiple stellar companions constantly flexes a star's interior. This mechanical stirring disrupts the normal flow of plasma, twisting and strengthening the magnetic fields that rise to the surface, forcing them to concentrate their energy into fewer, far more powerful nodes. The star becomes a roiling cauldron of magnetism, its surface a patchwork of these dark, magnetic islands, but the strangest possibility is that this activity may not be random. In a system so intimately linked, the magnetic cycles of different stars could become synchronized. Imagine two stars in a tight binary, their interiors tidally agitated by each other's proximity. Their magnetic dynamos, both operating under this shared gravitational rhythm, might eventually fall into step. Their activity cycles, the periods where starspots wax and wane, could lock together, rising and falling in tandem like a cosmic heartbeat. This synchronization could even extend across the hierarchy through resonant gravitational nudges, or via the intertwining of their magnetic fields in space. We might one day observe a Tredecuple system where the starspot activity on 3 or 4 different members pulses in a strange, shared harmony, a chorus of magnetic storms conducted by the gravity that binds them all. This turns the entire system into an interconnected electrical grid, where a flare on one star might induce activity on another, not through proximity, but through a fundamental coupling of their hidden internal clocks. The surfaces of these 13 suns can hold the ghosts of their dead siblings. This is the hidden legacy of stellar cannibalism, written not in light or gravity, but in chemistry. When a star in a tight binary spills its atmosphere onto a companion, or when a supernova detonates within the crowded family, it does more than just flash and recoil. It sprays the surrounding space with a cloud of newly forged elements, a cosmic fallout that rains down on every star in its path. Astronomers see the evidence for this in the star's spectral fingerprints, in the bizarre and unexpected abundances of specific elements on their surfaces. They find stars that should be rich in hydrogen and helium, the basic fuels of fusion, but are instead curiously polluted with heavy elements like carbon, barium, or strontium. These are not elements the star created itself through its own internal nuclear processes. A normal star's internal furnace produces heavier elements deep in its core, but those elements remain trapped there, buried under layers of lighter gas. The only way for them to appear prominently on the surface is if they were dumped there from the outside. Imagine a pristine white beach. Now picture a wave washing over it, leaving behind a scattering of dark metallic sand. That is what happens to a star when it is polluted by a companion's death throes. One of the most telling signatures is a barium star. Barium is a heavy element forged in the slow S process, a neutron capture chain that occurs deep within aging giant stars. For a smaller, main-sequence star to have a barium-rich atmosphere, it must have been showered with material from a giant companion that has since died and shrunk to a faint white dwarf. The living star now wears the ashes of its former partner like a chemical tattoo. In a Tredecuple system, this cross-contamination could be a widespread phenomenon. A supernova from one massive member would not just fling its outer layers into the void. It would bombard every other star in the system with a wave of iron, nickel, silicon, and radioactive elements. A violent merger in one tight binary could eject a cloud of carbon-rich debris that slowly drifts across the system, dusting the surfaces of distant stellar cousins over millennia. The result is a chemical tapestry where no star's composition is entirely its own. Each one carries a blended history of the entire family's most violent events. By reading these elemental signatures, astronomers can perform a form of celestial archaeology. They can look at a star with a strange overabundance of carbon and deduce that, billions of years ago, it had a close binary partner that went through a helium-burning phase and dumped carbon onto it before fading away. They can find a star enriched with elements from the rapid R process, like europium or gold, and trace that back to a neutron-star merger that happened within the gravitational bounds of the system long ago. This turns the entire 13-star clan into a cosmic chemistry lab, where the most catastrophic experiments leave permanent stains on the participants. The light we see is a blend, but the chemistry reveals the individual scars, the hidden stories of sacrifice, theft, and fallout that have shaped each sun's very essence over eons. This intricate gravitational clockwork keeps time with astonishing precision. The orbital period of a tight inner binary, the frantic heartbeat at the system's core, should be a metronomic constant. Yet in a Tredecuple star system, it is anything but. The ticking of this cosmic clock speeds up and slows down in subtle, predictable rhythms. This is because the dance of the central pair is not performed in empty space, but within the shifting gravitational field created by the other 11 suns. As those outer stars move along their own grand orbits, their combined pull tugs on the inner binary, sometimes giving it a slight gravitational push forward, sometimes a gentle break. Imagine two figure skaters spinning in a tight embrace at the center of a vast circular rink. Now picture 11 other skaters gliding in slow, majestic circles around them. As those outer skaters pass by at different points, their subtle gravitational influence, their mere presence, will ever so slightly alter the spin of the central pair, making them whirl a tiny bit faster or slower. Astronomers detect this not by watching the stars directly, but by listening to the clock of their eclipses. They have spent decades, sometimes over a century, meticulously recording the exact moment one of these inner stars passes in front of its partner, blotting out its light. Over time, they plot these eclipse times on a graph. If the orbit were perfectly stable, the points would form a straight line, each eclipse occurring exactly one orbital period after the last. Instead, what they see is a beautiful, wavy curve. The eclipses arrive slightly early for a while, then trend late, then early again, tracing out a sinusoidal wave that can have a cycle lasting years or even decades. This phenomenon is called eclipse timing variations, and it is one of the most powerful tools in the astrophysicist's kit. Each wave in that curve is a direct message from a hidden perturbing body. The period of the wave tells you the orbital period of the distant perturber, the object causing the timing shift. The amplitude of the wave, how early or late the eclipses get, reveals the perturber's mass. By disentangling multiple overlapping waves in the timing data, astronomers can literally map the orbits and weigh stars they have never seen. A long, gentle wave with a period of 50 years might point to a distant, massive binary orbiting the inner pair. A shorter, sharper ripple superimposed on top of it could betray the presence of a closer, lower mass star. Through this method, the entire 13-star system reveals itself not as a static picture, but as a dynamic gravitational symphony, with each unseen player announcing its presence through its precise influence on the central metronome. This turns the system into the universe's most exquisite clock, where every tiny variation in the tick is a chapter in the hidden story of its makers. The universe has already proven it can forge worlds in the most hostile of stellar neighborhoods, far beyond the pandemonium of a Tredecuple system. In the ancient core of a globular cluster, a planet endures a far stranger existence. It orbits a binary pair consisting of a pulsar, a rapidly spinning neutron star that beams radiation like a cosmic lighthouse, and a white dwarf. This world, known as PSRB 1620-26b, or the Methuselah planet, is over twice as old as our Earth. Its very existence is a defiant statement. If a planet can form and survive the violent supernova that created its pulsar host, and then persist within the dense gravitational soup of a globular cluster, then perhaps planets are not impossible in other extreme environments. This discovery forces us to reconsider the outer frontiers of a Tredecuple system. The inner realms are a collisional hellscape but move far enough out, and the chaos begins to average into a strange kind of order. From a distance of perhaps hundreds or thousands of astronomical units, the 13 individual stars blur into a single, combined point of light and gravity. Their frantic orbital dances become irrelevant, their eclipses and flares smoothed into a steady, composite glow. In this distant, frozen realm, a planet could, in theory, trace a vast, slow circle around the entire stellar clan. The concept of a habitable zone here becomes a geometric marvel. Instead of a ring around a single sun, it would be an immense spherical shell centered on the system's combined center of mass. Within that shell, a planet would receive a constant, blended warmth from all 13 stars. Its daylight sky would not feature 13 distinct suns, but a single, small, brilliant patch of merged light, a luminous jewel holding every color of its stellar components. The conditions on such a world would be unlike anything we know. A single year, one orbit around its 13 suns, could last for millennia. Seasons would not be dictated by a tilt, but by the planet's slow journey through any slight variations in the shell's temperature. More critically, the light itself would be profoundly different. The blended radiation from stars of vastly different temperatures would create a spectrum unlike that of any single star, rich in some wavelengths and deficient in others, posing a unique challenge for any potential photosynthesis. Yet the very distance that makes this orbit possible also creates its greatest irony. While the averaged light might be steady, the gravitational stability at such a range is incredibly fragile. The planet would be barely bound, a distant satellite on the very edge of the system's gravitational influence. A close pass by another star from outside the clan, or a strong gravitational recoil from a merger within, could easily strip it away, sending it wandering into the interstellar dark as a free-floating orphan. The Methuselah planet shows us that planets are survivors capable of enduring unthinkable violence. Its existence whispers a tantalizing possibility that in the silent, frozen dark at the edge of a 13-star system, another ancient world might also be tracing its millennial path, basking in the gentle, combined glow of a family of suns it never truly knows. This relentless gravitational kneading could forge a world of pure fire. For any captured moon or planet unfortunate enough to orbit a star locked in a tight binary, the concept of a stable surface vanishes. The tidal forces we see flexing stars would act upon a rocky body with apocalyptic ferocity. Imagine a world like Jupiter's moon Io, where tidal heating from the giant planet drives hundreds of active volcanoes but amplify that effect by 1,000. Here, the primary source of heat is not internal radioactivity, but the constant, rhythmic stretching from two nearby suns. As the planet orbits its host star and that star whips around its binary companion, the gravitational pull shifts from multiple directions in a complex, overlapping rhythm. This doesn't just create a hot core, it churns the entire planetary interior into a molten frenzy. The crust, unable to withstand the stress, would shatter and submerge into a global magma ocean. This is the theoretical end state, a plasma planet. Its surface would not be solid rock, but a perpetual, incandescent sea of molten silicate and metal, temperatures soaring to many thousands of degrees. The atmosphere would be a thick, toxic haze of vaporized rock, glowing from the heat below and the intense light from its multiple suns. Such a world would have no mountains, no valleys, no permanent features at all. Instead, its face would be a dynamic canvas of gravitational art. The tidal bulges raised by the stellar dance would manifest as continent-sized waves in the magma ocean, slow-moving swells of liquid rock cresting and falling in rhythms set by the orbital periods of its tormentors. If a third distant star's gravity adds its own periodic tug, these waves could interact, creating interference patterns, peaks and troughs of molten material that might rise and fall over centuries. Lightning would flash continuously in the metallic vapor above, and the sky would forever rain droplets of iron and silicates that sizzle back into the global ocean. This is not a world of geology, but of fluid dynamics on a planetary scale. While no such object has been observed, its possibility stretches our understanding of what a planet can be. It represents the ultimate expression of tidal violence, a place where the gravitational music of 13 suns is written in waves of fire and plumes of glowing atmosphere. If it exists, it is less a planet and more a temporary, coherent storm in the chaos, a droplet of liquid rock held together by its own gravity, dancing until the music changes and it is torn apart. The gravitational engine of a 13-star system does not operate in isolation. To understand its true purpose, we must zoom out to see the sprawling stellar nursery it was born within. Tredecuple systems are not random accidents scattered through empty space. They are almost exclusively found within, or are the final remnants of dense open clusters. These are the bustling stellar cities of the galaxy, where thousands of stars are born together from a single giant molecular cloud. In this crowded metropolis, the system of 13 becomes a central gravitational power plant, a dynamical engine that fundamentally reshapes its entire neighborhood. Its formation itself is an act of violence, likely the result of runaway mergers and captures in the cluster's densest core. Once established, this massive, complex family becomes the dominant gravitational player in the local area. Its sheer mass and intricate motions act like a chaotic pendulum swinging through a room full of marbles. As other, simpler stars and binaries drift past, they feel the system's combined pull. These encounters are rarely gentle. A single star passing too close might receive a gravitational slingshot, accelerating it to such a speed that it is ejected from the cluster entirely, thinning the stellar population. More importantly, the Tredecuple system acts as a binary hardening factory. When a normal binary star pair drifts into its sphere of influence, the complex gravitational tides can steal orbital energy from it. This process, called dynamical hardening, shrinks the binary's orbit, making the two stars whirl around each other faster and closer. The energy taken from that binary doesn't vanish, it is transferred, often helping to stabilize the orbits within the Tredecuple system itself or flinging another star away. Over millions of years, this relentless gravitational processing has a profound effect. It scatters stars, sending some to the cluster's outer halo and others into the galactic wilderness. It creates a population of exceptionally tight, hardened binaries in the cluster's core, and eventually, through its own internal ejections and the recoil from countless encounters, the Tredecuple system itself may be expelled. What we sometimes find drifting alone in the galactic disk, then, is not a primordial family but a refugee. It is the surviving core of a once great stellar community, a gravitational engine that ran until it consumed its own fuel of surrounding stars and was spat out by the very cluster it helped to evolve. The distribution of stars we see in ancient, settled clusters, their missing middleweight stars, their centralized tight binaries, can often be traced back to the brief, violent reign of a monstrous system like this, a temporary king that ruled through chaos before being dethroned by the physics it mastered. Predicting the future of a 13-star system is a battle against chaos itself. To peer ahead, astrophysicists turn to the raw power of supercomputers, running what are known as n-body simulations. Each star is reduced to a point of mass, a gravitational actor on a digital stage, with the laws of physics programmed as the only script. The task seems straightforward. Calculate the gravitational pull of every star on every other star, move them forward a tiny time step, and repeat billions upon billions of times. Yet this is one of the most notoriously difficult problems in all of science, a perfect example of deterministic chaos. The system is so exquisitely sensitive that the tiniest rounding error, a change in a star's starting position by less than the width of an atom, will lead to a completely different outcome a million simulated years later. It is the ultimate butterfly effect, where a flap of a butterfly's wing on Earth could, in theory, determine which star gets ejected from a system 1,000 light-years away. Watching these simulations unfold is to witness a cosmic ballet of pure mathematics. Visualizations show stars not as simple orbs on circular tracks, but as threads weaving through a complex braid. They trace out mesmerizing, looping rosettes, their paths intertwining in temporary harmonies that can last for thousands of simulated years. You might see a pair of stars locked in a stable resonance, their orbits singing in gravitational harmony, while a third dances at a Lagrange point that shouldn't exist. For a long, beautiful moment, the entire family appears to have found a perfect, stable configuration, a clockwork that could last forever. Then, without any external trigger, the clockwork shatters. A subtle resonance builds over centuries. A distant star receives one gravitational nudge too many, and the entire structure unravels in a breathtakingly short span of time. One star is flung out on a hyperbolic arc, screaming into the digital void, its departure sending shockwaves through the remaining members. Orbits that were stable for millennia suddenly become wildly elliptical, leading to a close pass, a tidal disruption, or a merger that resets the entire simulation. The most profound lesson from these digital experiments is not a prediction, but a humbling admission of ignorance. We can run the same simulation 1,000 times with imperceptibly different starting conditions, and we will get 1,000 different endings. In one run, the system might eject half its members and settle into a quiet sextuple. In another, it might hold together for billions of years. In a third, two tight binaries might spiral inward and collide in a cataclysmic flash that obliterates the hierarchy. The long-term fate of any real Tredecuple system is not just unknown, it is fundamentally, chaotically unknowable. These simulations are not crystal balls, they are maps of possibility. They show us that within the apparent clockwork of the cosmos lies a deep and irreducible randomness, a reminder that the universe retains the freedom to surprise itself. The universe's most chaotic families are also its most prolific dust producers. Peering into these 13 star systems with the infrared eyes of telescopes like Spitzer and the James Webb Space Telescope reveals a startling signature, a massive excess of infrared light. This is the thermal glow of countless trillions of dust grains, each one warmed to a few hundred degrees by the combined starlight of 13 suns. The sheer scale of this dusty shroud is staggering, often containing more solid material than our entire solar system's asteroid belt. This dust is not the pristine, primordial stuff from which stars form. It is second-generation debris, the pulverized remains of a violent history. The relentless gravitational tides within the system act like a cosmic grinder. They stir up any population of asteroids, comets, or dwarf planets, driving them into catastrophic collisions at incredible speeds. These are not gentle mergers that build new worlds, but shattering impacts that reduce mountains to fine powder. Each collision creates a cloud of vaporized rock and ice that rapidly cools and condenses into microscopic grains, a fresh infusion of dust into the surrounding space. This process turns the entire volume of the Tredecuple system into a short-lived but incredibly productive dust factory. The intense radiation from so many stars, however, creates a constant tension. While new dust is being made, the stellar winds and photon pressure are simultaneously blowing the finest grains away, sweeping them out into the wider interstellar medium. This gives the dust a fleeting existence, perhaps only lasting for thousands or millions of years before it is entirely scoured away, only to be replenished by the next major collision. What does this mean for the galaxy? These systems become localized engines of material processing. They take large, rocky and icy bodies and grind them down into fine particulate matter, enriching their immediate surroundings with a fog of silicates, carbon compounds, and water ice. When this dust is eventually expelled, it carries these processed materials into the void, where they can one day become part of new molecular clouds, new stars, and perhaps new planets. The dusty glow we see is more than just a byproduct of chaos. It is the signature of a system actively recycling itself, turning the wreckage of failed worlds into the seeds for future cosmic generations. That dusty glow is a signature of recent violence, but what if some of these stellar explosions were witnessed by human eyes? The night sky our ancestors watched was not a static painting. Chinese, Korean, Arabic, and European astronomers meticulously recorded the sudden appearance of guest stars, points of light where none existed before, that shone for weeks or months before fading away. While many are now identified as supernova, like the Crab Nebula's birth in 1054, others remain enigmatic. Could some of these temporary stars have been cataclysms within a nearby Tredecuple system? A nova, the thermonuclear flash on the surface of a white dwarf stealing from its companion, could certainly fit the bill. From a few thousand light-years away, such an eruption in a 13-star family would appear as a brilliant new star in a familiar constellation, visible even in daylight for a time. But a nova is a surface explosion. It does not destroy the star. An even more dramatic and rarer event would be a stellar merger. If a tight binary at the heart of such a system finally spiraled in and collided, the resulting red transient could outshine a nova by orders of magnitude, blazing for months as a brilliant red or orange new star before fading to a husk. The key is cross-referencing. Astronomers take the known positions of candidate Tredecuple and other high multiplicity systems and scroll back through the historical records. They look for a guest star annotation in the right patch of sky, with a described duration and brightness that matches a theoretical nova or merger's light curve. The distance is critical. The system must be close enough for the eruption to have been visible to the naked eye, likely within 5,000 or 6,000 light-years. Imagine a court astronomer in 11th century Cairo or Song Dynasty China, noting a new star near the tail of Scorpius. They had no idea they were documenting the final, glorious embrace of two stars in a family of 13, a flashbulb moment illuminating a cosmic drama that began billions of years earlier. Finding such a match would be a breathtaking link between ancient human observation and the most extreme stellar mechanics, turning a historical footnote into a precise timestamp for one of the universe's most chaotic events. The census of these stellar families reveals a curious and persistent absence. Red dwarf stars, the most common suns in our galaxy, seem to vanish from some Tredecuple systems. These small, cool, and incredibly long-lived stars outnumber every other stellar type combined, forming the silent majority of the Milky Way. Given their sheer abundance, you would logically expect them to be frequent members of these sprawling stellar clans, perhaps as the quieter, stable anchors in the chaotic hierarchy. Yet when astronomers take a detailed inventory, some of these 13 star systems appear suspiciously clean of red dwarfs. It is a statistical ghost, a missing population that should be there. Where did they all go? The leading theory points directly to the violent nursery where these systems are forged. In the dense young star cluster, gravitational interactions are a game of survival of the fittest, or more accurately, the heaviest. When multiple protostars are jostling in a tight space, the lower mass red dwarfs are at a severe disadvantage. They are like lightweight balls in a chaotic game of gravitational pinball, easily battered around by their more massive siblings. During the system's tumultuous early assembly, a close encounter with a heavier star can impart enough energy to fling a red dwarf clear out of the gravitational family entirely, casting it into the wider cluster or interstellar space before the system's final hierarchy even settles. This preferential ejection would leave behind a system dominated by more massive stars, a kind of gravitational filtering that skews the family's demographics. But there is another, quieter possibility. Perhaps the red dwarfs are not missing at all, but merely hiding. Their low mass and dim light make them incredibly difficult to detect, especially if they occupy the outermost, slowest orbits in the system's vast gravitational domain. From thousands of astronomical units out, a solitary red dwarf would exert only the faintest gravitational tug on its brighter siblings, and its meager glow would be utterly drowned in the combined light of 13 suns. It could be a silent, dark sentinel orbiting the entire chaotic core, invisible to our current instruments, waiting for technology sensitive enough to whisper its presence. This missing dwarf problem is more than a census anomaly. It is a clue to the brutal formative years of these systems. The absence tells a story of a violent sorting process where the smallest members were the first to be exiled, leaving behind a family shaped not just by gravity but by a kind of cosmic selection. The gravitational web of 13 suns can bend the light of the universe itself. Among the rarest signatures such a system could leave is a phenomenon called gravitational microlensing. This occurs when the entire massive clan drifts across our line of sight to a far more distant, single background star. According to Einstein's theory of general relativity, mass warps the fabric of spacetime and light must follow those curves. As the Tredecuple system passes in front, its immense combined gravity acts like a complex, shifting lens, distorting and magnifying the background star's light in a way no single star ever could. The result would not be a simple brightening and fading. Instead, the light curve would be a chaotic masterpiece, a wild scribble of peaks and valleys. Each individual star in the system, along with every binary and triple combination, would create its own tiny, moving warp in spacetime. The background star's light, traveling through this warped landscape, would take multiple paths around the various masses, creating multiple, distorted images of itself that our telescopes could never resolve, but whose combined effect would produce an insane pattern of magnification. The central tight binary might cause a sharp, double-peaked spike. The wider, slower moving pairs would imprint longer, gentler waves upon the signal. Even a faint, hidden red dwarf in a distant orbit could betray its presence through a subtle, extended bump in the curve. This light curve would be a unique gravitational fingerprint, a direct encoding of the masses and positions of all 13 components at that moment in time. Decoding it would be the ultimate challenge, but the prize would be unparalleled. A direct, model-independent measurement of the mass of every single star in the system, including those too dim or too close to be seen by any other means. It would be like suddenly having an X-ray vision that reveals not just the bones, but the precise weight of every bone in a living creature's body. While such a perfect alignment is astronomically improbable and has not yet been observed, it remains a thrilling possibility for future sky surveys that monitor millions of stars continuously. One day, an automated alert might flag a star in the galactic bulge beginning to brighten in a strangely complex way. As astronomers rush their telescopes to observe, they would witness not just a lensing event, but a cosmic autopsy, reading the precise mass and structure of a 13-star family from the twisted path of a single beam of ancient light. A supernova within a 13-star family is not an ending, but the first domino to fall. The initial explosion is a cataclysm of unimaginable scale, the death scream of a massive star. In an instant, its outer layers are blasted into space at a significant fraction of light speed, a shockwave of stellar debris screaming outward. But for the surviving 12 siblings, the greater violence is silent. The star that just died, which held a precise gravitational weight in the delicate orbital dance, suddenly vanishes. Up to a quarter of its mass might be ejected in the blast, with the core collapsing into an ultra-dense neutron star or black hole. This is not a gentle removal, it is a sudden, severe amputation of gravity from one point in the system. The intricate clockwork instantly goes haywire. Every orbit that depended on that star's precise pull is now unmoored. Stable paths become chaotic ellipses, gentle resonances turn into destructive beats. Stars that were once kept at a safe distance by the dead star's influence may now find themselves on collision courses. Binary pairs, their balance shattered, might spiral inward toward merger. The entire hierarchy receives a violent gravitational jolt. Yet this is only the prelude. The system now contains a new, monstrous object, a neutron star or black hole, a gravitational pit of infinite depth. Its presence alters the physics of every subsequent interaction. If the first supernova did not tear the family apart, it sets the stage for a far more dangerous era. The survivors now dance around a hidden abyss. Decades, centuries, or millennia later, another massive star reaches its end. It too goes supernova, but this second explosion happens within a system already traumatized and rearranged. The shockwave from this new blast now plows through orbits that are already stressed and chaotic. More critically, if the second dying star is in a binary with the first-born neutron star, the consequences are apocalyptic. The supernova explosion in such a tight binary can receive an extra kick, potentially ejecting the newborn neutron star at incredible speed like a bullet from a rifle. The recoil could disrupt the entire central core of the system. Alternatively, if the binary survives, you now have two compact objects whirling around each other, a perfect gravitational wave generator destined to merge. This sequence can cascade. One supernova triggers orbital shifts that hasten the evolution and death of another massive member, which then explodes and further destabilizes the system, creating a chain reaction of stellar death. The end game of such a family is written in the darkest ink of the cosmos. The most likely final state is a small, grim cluster of neutron stars and black holes, the dead cores of the once bright family, locked in a final, slow gravitational waltz that will eventually decay through the emission of gravitational waves, leading to mergers that send ripples through spacetime itself. In other simulations, the chain of explosions provides enough cumulative kick to completely unbind the system. The remaining living stars are flung away on divergent paths, and the stellar corpses are scattered into the galactic halo, becoming solitary wanderers. The glorious, intricate dance of 13 suns ends not with a whisper, but with a series of thunderclaps that echo across millennia, leaving behind only ghosts and the memory of light. From supernova chain reactions to gravitational pinball, these 25 discoveries paint a portrait of cosmic chaos refined into a temporary, breathtaking order. Tredecuple star systems are not merely astronomical curiosities. They are fundamental physics laboratories operating on a grand scale. They push our theories of gravity to the breaking point, forcing us to model dances of 13 bodies across billions of years. They rewrite the rules of stellar evolution, showing us families where stars are captured, consumed, and chemically tattooed by their siblings. They challenge our very ideas of where planets can exist, suggesting worlds of molten rock or distant, frozen orbits under a blended, singular sun. The overarching theme is one of beautiful, violent contradiction, stability forged from chaos, and ephemeral harmony born from relentless gravitational negotiation. Every strange detail, from the missing red dwarfs to the synchronized starspot cycles, reveals a deeper layer of how the universe organizes matter under the most extreme conditions. Our journey through these points of light is about to leap forward. The next generation of observatories like the Vera C, Rubin Observatory and the Laser Interferometer Space Antenna will peer deeper into this chaos. They will detect the faint gravitational hum of these systems, directly image the warped debris disks, and perhaps even catch the flash of a stellar merger in real time, turning these cosmic mysteries into detailed maps. So we turn the question to you: which of these 25 discoveries captivated you the most? Was it the plasma planets with oceans of liquid rock, or the silent exile of hypervelocity stars? Do you think any form of life could ever cling to existence in such a radiant, turbulent environment? Share your thoughts and speculations in the comments below. If unraveling the deepest mysteries of the cosmos lights up your curiosity, consider subscribing for more journeys to the edges of our understanding, where every point of light holds a story waiting to be told.